Our next speaker is Mike Sparrow. He's CEO, CTO at Active Group, co-organizer of the annual Bob Conference, Developer Conference, and expert in functional programming. He has about 20 years of experience in teaching programming in high schools, universities, and other contexts. In his talk, Mike will share his experiences and gives us an idea on how changes in culture, methods, and tools in programming might contribute to the future of software and the software of the future. Please enjoy the talk by Mike. The stage is yours.
Thank you very much. And did she say 20 years? I'm older than that. So I appreciate you staying up this late. So I'm all grown up now, so talk about growing up. So I graduated at some point and got a degree in computer science. I got a PhD many years ago, and now I'm CEO of a software company that carries some actual responsibility. But as I was preparing this talk, I thought back to the past, and it happened to be the year 1983 when I started hacking. And, well, I wasn't there, but it must have been the year of 1C3, right? And so if you read what was written about the computing revolution that was to come in the early 1980s, a lot of what we're having arguments about today was already there. Computer security, data governance, surveillance, all these things were already on the radar of the media back then. But a couple of things were different also. So here's a major German news magazine that had an article on computers in children's rooms. And not everybody had a computer back then. So if you were a kid like me who was interested in learning about computers and didn't have one at home, there was a place you could go to, which was the local department store. And, well, the picture isn't very clear, but that's actually a local department store that had rows and rows of home computers set up and plugged in and ready to go for children to play with. And so back then there were, you don't remember this, but there were many different kinds of home computers. There was no internet. There was very little in the way of readily available literature on how to program computers. So we all had to figure it out by trial and error. And we didn't really have a good methodology of how to program computers. Now fast forward a couple of years, I looked unbelievably geeky in 1986, but I had my own computer, and that must have been even the second or third one that I had. And you know, by the time I was an exchange student in the United States, they made me president of the computer club. You can see another picture of me right there. And that was my first experience of teaching a formal course. So that was in 1988, and that was the end of that year. So that means I taught my first computer science course 30 years ago. And I then ended up designing the intro programming course at the University of Tübingen and taught that over more than 10 years. I taught programming to humanities majors. I've done a lot of professional training by now. And well, if you're sort of a compulsive educator like I am, everybody around you suffers, right? Your coworkers, your friends, my children, certainly my relatives. A lot of them have had to endure, you know, one or other kinds of programming course from me. So back then, as we were trying to figure out how to hack computers, you know, as there was very little available literature, we also looked for role models. And here's an early role model from the 80s, a man named John Draper, better known as Captain Crunch because he used a whistle that he found in a cereal box to manipulate the US phone system, and then actually went to prison for it. But John Draper also is not as well known for actually writing software, and he produced one of the early word processors that was available on personal computers called Easy Writer that I actually used. And there were reports on the prolific programming style that Draper practiced. So I don't know if you can read this. The joke is if Draper were writing math routines for addition and he came up with the answer 2 + 2 = 5, he would put a clause in the program. If 2 + 2 = 5, then that answer is 4. And that's generally the way he writes programs. Who's seen programs like this? Where, yeah, so a lot of you, right? Where somebody adds clause after clause of special cases until, you know, so the special cases encountered in the wild are all covered. So of course, you know, in 1983, we all figured it out ourselves, but people by 1985, the Hacker Bible came out, and already worried about how we would educate children about computers in the future. And so there was an article about computers in school, and I'm going to zoom in a little bit. And as I'm sure you've been involved in many discussions on how to teach programming to beginners, and as always, that discussion focuses on the programming language that's being used. And back then, the popular languages were somewhat different from today. There was BASIC, Pascal. BASIC had that reputation of producing spaghetti code. Forth is mentioned, Logo is mentioned, and C is mentioned there. And back then, a prominent professor of computer science in Germany said, well, as long as you don't program in BASIC, you'll be fine, right? The pure fact of not programming BASIC is going to keep you from writing spaghetti code. And as we now know, that isn't really true. And I'm sure most of you have seen really crappy and spaghetti code in production, but the bullets kind of keep hitting closer, right? I think this must have been 2 years ago when a vulnerability in popular IoT devices essentially brought down the internet because they were all assembled into a botnet that brought down a popular DNS provider, and GitHub went down. I think that's what most of you probably remember. There was Heartbleed that I'm sure a lot of you remember. Due to a vulnerability in a buffer overflow, because in OpenSSL, which was written in C, there was Equifax, which divulged a lot of social security numbers because of a bug in struts in the web framework that they used. And more interestingly, I think for students of the past, there was the Cloudbleed vulnerability, which would divulge secret passwords and account information on web pages just as part of the web cache. You wouldn't even have to ask it, secret questions as you would have to ask Cloudbleed. And that was oddly reminiscent of something, well, none of you remembers, unless you're as old as I am, which was the Btx hack, which was one of the founding stones, I think, of the Chaos Computer Club, where people were able to make the computer of a bank that was attached to BDX divulge passwords, essentially a memory dump that contained passwords, and then transfer a lot of money from that bank to them. And so that felt a lot. So the present, in many ways, it feels a lot like the past did. And you would think there would be some kind of progress. And I think I was as guilty of that as anybody. So in 1986, I wrote my first book. And as many books, now and then, it focused on a specific programming language. And of course, I picked like the worst programming language in hindsight that I ever could have picked, and that is responsible for a lot of the vulnerabilities that we see today. So, but again, it was, at least I can say it was in 1986, so it was a long time ago. So you would think things have changed. So some of you may have been at a talk earlier today about the Bob system for teaching young kids on how to program. And Bob prides itself on teaching programming in exactly the same way as computer experts would program, but it would use an approach based on gamification to teach students, right? And so, in 1986 we were programming in C, so Bob now is programming in C++. So something has happened since then. And you can look at a lot of pages, web pages, and systems for teaching beginners on how to program. So here's a prominent page supported by a lot of major organizations called StartCoding.de from this year. And you can see, again, that a lot of the stuff that it teaches, well, first of all, it's focused on particular programming languages, on Scratch and Python and processing. So there's 3 programming languages mentioned there. And if you can read the fine print, and if you can read German, it says spielerische Herangehensweise, which means that there's a fun-based, playful approach to teaching how to program. And that's common to a lot of things. So if you go to Kids Space, you will find a section there called Jugendhackt. And you can see that it also takes a very playful approach to teaching. And if you look at its material, a lot of it also features particular programming languages. And if you look, you will find that there's a curious absence of methodology on all of these pages. I think part of the reason is that I think if you teach programming, you can easily get the feeling that it's very easy, right? I mean, you can teach people to write very trivial programs that will blink an LED or do something like that. And the eyes of your students, they will just light up. And they will just love what you teach them if it's trivial. If it's not so trivial, so I like functional programming, which is sometimes not so easy. But in any given group that's large enough, you will find a few Sheldons that will just eat up everything that you teach them. And they will come to you and they will say, oh, I just love whatever it is, the lambda calculus, functional programming, whatever. And if you've been at it for 30 years, you notice that it doesn't really matter what you teach. You will always find a few Sheldons that will tell you that they love what you teach them. So after a while, you realize that, well, there's a few Sheldons, but then there's also a lot of students in your class who are not Sheldons. And well, as you're chugging along on your teaching train and you look out the back, you suddenly realize that you've left a lot of students behind. They might still like what you're doing, but you really haven't taught them any significant abilities. And so over the years, I've had a lot of opportunity to think why that is. Why is teaching so hard, and why is it often unsuccessful? And one of the reasons is that I think if you pick up almost any book on programming or open any web page that tries to teach you programming, it uses an approach that I call teaching by example. So here's a book by a computer science professor came out this year, and learn Java the easy way. And the easy way is in the second chapter, right after the introduction, we do an example, right? And there's a concrete listing of a concrete program. And the text essentially is just a commentary for that program. And then the expectation is that from the example that you've seen that exposes various elements of the programming language, like while loops and system out println and whatever, you will, I think by osmosis or some other magical mechanism, absorb the ability to apply the techniques to new problems. And my experience has been that that often does not work for the great mass of students who are not Sheldons. I thought back to the great teachers that I've had, maybe not in computer science, but what methods were they using? And then when I thought about it, I realized that they were using methods that were completely different. So here's a picture of my 11th grade English teacher, Anne Carvalho, in 1987. That was as I was an exchange student in the US. And at the beginning of the class, she handed out a piece of paper. Well, you can't really see it, so I'm going to zoom in. That said, how to write a composition in this class, right? And so, composition of this class, well, here's the second section is the body, right? The body is 3 paragraphs, with each paragraph developing one of the areas of the thesis. First area scope, usually 1 paragraph, transition, topic, sentence. If you look at this, this is a very precise outline that explains the function of just about every single sentence in your composition. So it's a very rigid harness, if you will, for your composition. And coming from Germany, Germans are generally they don't accept a lot of power distance, and they don't like authority that much. I was an instant rebel to this concept, and it took me most of the year to really accept that it was a great way to learn to learn one good and working way of writing a composition, and then I could branch out from there and develop other working ways of composition. So this is a methodology for doing something that is extremely useful and powerful when you teach. And you might say, well, we have methodologies like that in computer science and in programming as well. We've been doing object-oriented programming, which is supposed to be very principled. But I've seen a lot of crappy object-oriented code as well. I don't know about you. So, and object-oriented programming, well, it has encapsulated state, it has polymorphism, and it has inheritance. Inheritance is particularly bad because there's so many different uses of inheritance, and typically your programming language will only have one mechanism, and so people often get it wrong, and they do inheritance the wrong way around, and there's empirical studies, but there's many other ways in which object-oriented software sort of ends up looking like this. So anyway. So, this is not supposed to be an indictment of the hacker culture. We see a lot of things, around here that look like this, and they're wonderful. But they're no substitute for, methodologically sound development of software. So, well, many years ago, I thought there has to be a different way, and I got together with a man called Matthias Felleisen, who happens to be a fellow German bureaucrat just like me, but who lives in the US and who wrote a book called How to Design Programs, which you can find online if you're interested. You don't even have to buy the paper. And we kind of did sort of a German version of that, working with Matthias, called Dein Programm. which also has a free book on it. And the overarching principle of that approach is that we try to be systematic about everything, so that we try to attach systematic fixed plans or system to every step of program development. And these things are called design recipes. It was a name invented for this. So I guess I'm gonna torture you with one concrete example, a classic example. So Matthias was in Texas at the time. The classic example is animals on the Texas highway. And we're going to concern ourselves with two kinds of animals. So there's an armadillo on the left, and there's a rattlesnake on the right, and there's, of course, the highway in the middle. Okay? So we'll start out with armadillos, and for the purpose of this application, you might just describe armadillos. So what's important about armadillos, here you will see why, is an armadillo has the following properties. It's alive or dead, and it has a certain weight. And so I'm going to greatly shorten this process of systematic development here, but what we say is, well, if you find yourself describing your data, this is a data-centered approach, if you find yourself describing your data with words like, it has the following properties, or it consists of the following parts, then you're dealing with something called compound data. So this is a fixed part of the plan, and it has a name. And it's very important to give names to things so you can talk about them. And so once you've identified that you're dealing with compound data, you can model that data and you can translate that model into code. And here you see a screenshot of a system called Dr. Racket, which is a programming environment that was developed for beginners. And you can see a little program fragment in a programming language also developed for beginners. In fact, that fragment was developed for beginners that says, well, in the interest of brevity, we're abbreviating armadillo to Dillo. So it says, well, we're dealing with Dillo, so we're calling the data type, if you will, we're calling that Dillo. If we're dealing with compound data, we need one way to construct it, so we need a constructor. And so we're going to call the constructor makeDillo. We'll see later that we'll need one way of distinguishing Dillos from other things, so we'll need what's called a predicate. Ignore that for now. And on the previous slide, or here in the data definition, the comment that is in yellow, you saw that an armadillo has two components. It has two parts, and therefore there need to be two, if you will, getter functions, and those are called Dillo alive P and Dillo weight. Never mind all those parentheses, at least not for the purposes of this presentation. Oh, and one more detail maybe is that if you look here, it says language. Dr. Racket is a programming environment that has many different programming languages, and this particular one, as I mentioned, is called Die Macht der Abstraktion, which identifies one particular set of programming language levels for beginners. Now, once you have that record definition, you can immediately call the constructor to go to make examples. So here's two example armadillos. And so you see these two expressions, makeDillo, and this hash mark T means true. So makeDillo true, and 10 means, well, we have an armadillo where alive is true, and the weight is 10, so that might mean an armadillo that's alive and weighs 10 kilos. And then there's another armadillo that, well, alive unfortunately is false, so it's probably dead, and it weighs 12 kilos. And the defines there just say, well, we're going to call the first one D1 and we're going to call the first one D2. Okay? And so one way to talk about these functions that we've created is by writing down what we call signatures. They're almost type signatures, not quite, that say what these functions behave like. So the constructor function that you just saw applied is called makeDillo. And in these funny programming languages, most things are written in prefix notation. So makeDillo accepts a Boolean and a number. Remember, that was the alive thing. Is it still alive? And the number that says how heavy it is. And it produces a Dillo object. And the Dillo alive and Dillo weight getter functions both accept a Dillo object. And the first of them says whether the Dillo is alive or not. So it produces a Boolean. And the second one produces a number that is the weight of the Dillo. Okay. So why is this all relevant? Life on the Texas highway is animals get run over by cars, right? And so we're going to write a function that simulates that process. So that thing in green is what we call a problem, a short statement on the short comment on what the function does that we're about to write. So we're going to run over an armadillo. Then it says, well, we're going to write a function called run over armadillo, and it goes from Dillo to Dillo, which means, well, the Dillo is not really a Dillo. It represents the state of the Dillo before it gets run over, and then one comes out of the right on the right-hand side. that says what the state is after it got run over by a car. Okay? And then you can write, so you can see all these things are sort of required elements of the curriculum. I'm going over them very quickly. The two next things are example and test cases at the same time. So check expect says, well, if we run over that first armadillo, it was still alive, it weighed 10 kilos. After we've run it over, it's dead and it still weighs 10 kilos. Okay? And the second test case says, well, if we run over D2, it is already dead. So after that, it's still going to be dead and it will weigh 12 kilos. Now, from the signature above, we already know what the function is called and how many arguments it has. It has one argument. So we can write something down mechanically that is what we call a skeleton, which is that thing in the beginning, the thing at the bottom. So we're writing a function or something called run over dillo. Lambda says that it's a function, and D says, well, that dillo up there, it's going to be called D here. This is a mechanical process. And so we see here how that is elaborated. We can do more things mechanically from this because Dillo is compound data. And whenever we accept compound data as input, we probably need to look at the parts to do anything that's meaningful. So we might as well call the two getter functions. So there's Dillo alive of D and Dillo weight of D. And also compound data comes out as output. And so we probably need to call the constructor in order to construct the Dillo that it's supposed to come out the right-hand side. So all of these things can be written down. And we ask our students to write all this stuff down and also actually write down those ellipses marks, the 3 dots. And these are building blocks and they are completely mechanical. They have nothing to do with the actual purpose of what we're doing. And then usually it's pretty easy to then fill in the missing steps and say, well, we are not really interested in whether the Dillo was alive or not before. But we are interested in the weight in constructing that new armadillo, and this is the run over function that does that. So you can see that there's a lot of steps. It's an extremely bureaucratic process producing that program, and some of those steps are completely mechanical. They might be boring, but they enable everybody to make progress. So you might imagine, I said rattlesnakes, and rattlesnakes are very similar to Dillo, so I'm going to run over those very quickly. So rattlesnake has the following properties, thickness and length, and you can see there's a record definition. There's a bunch of signatures that come out of that. We can do a purpose statement that says, oh, we're going to run over a rattlesnake now. We can't just do armadillos. There's a couple of test cases, and rattlesnakes get run over. They get flattened out, so their thickness goes down to 0 when they get run over. But the important thing is now, we might think about, well, we're just going to run over whatever animal comes under our wheels next. So we're interested in an animal on the Texas highway, and an animal is one of the following. It's either an armadillo or a rattlesnake. And whenever you see that wording, it's one of the following, or it's this or that or that or that, you're dealing with something that we call mixed data. And so, again, this thing has a name. And with mixed data, again, there's a fixed set of steps that you go when you program to them. So you define a signature that says, well, animal is a signature that's mixed from Dillo and rattlesnake. And we're then going to write a function that runs over an animal. And so it doesn't have Dillo to Dillo, or it doesn't have rattlesnake to rattlesnake. It has animal to animal. It has test cases like as before. And well, remember that there were 2 different kinds of animals on the Texas highway. And we need to treat them differently, right? It's a different thing of running over an armadillo and running over a rattlesnake. So for that, we need a conditional, and we need this predicate function that says, well, that animal A, is it an armadillo or is it a rattlesnake? And then we need to fill in the gaps. And of course, we've written those functions already, so it gets pretty easy. I don't know if you've seen this, and I've run over this very quickly, and I've left out a lot of steps. This is an extremely bureaucratic process. And when you read about this at first, you think, this is so boring. I can't, you go like this, right? And interestingly, if you practice this on your students, surprisingly, pretty quickly they go like this, because they realize that this bureaucratic approach actually makes them produce a working solution on their own. Some of them can't believe it, that it's successful, but then they start smiling. But it took a long, long time to develop this approach. So Matthias has been at it, I think, since the early 1990s. I've really been involved in this process, I think, since about 2001. So really you need to take an approach to teaching. You need to observe how well it does. And I can't stress this enough. When you observe, it is not enough to measure the popularity of what you're doing. It's not enough to ask your students, do you like this stuff, right? Is that something that's interesting? I've seen a huge bandwidth of things where we were unsuccessful, but people just liked it. People just liked it fine. And so, and that's this process. We repeat it many times, and we're hopefully going to repeat it many times in the future. So, but it has produced the following insights. So it's very useful to have a very bureaucratic approach to programming that we call design recipes. I didn't much talk about the fact that it's very helpful to have programming languages that are specifically developed for beginners or for learners. It doesn't have to be beginners. And it also has to have a programming environment that was designed for beginners. You can go either to a page called Program by Design or to Dyn Program, and you'll find a lot of information about that. But it took a lot of work, and it's usually it's not enough to just take your professional programming language and stick it on your kids. It might work for trivial programs, but it's not going to scale anywhere. So it's about growing up, but I guess this one is about growing down. So I think the progression really should lead us from the C and C++ like unsafe languages and all the hacking of the past, and that we like to use when we make exploits, to safe languages and runtimes. And finally, we're seeing something like Rust and ATS coming up. I really only know how to do this bureaucratic and systematic approach to programming with functional languages. And if you've watched this closely, you saw that what we did was type-driven, right? We looked at this, at the way our data is organized, and then organized our programs according to that data. Whether you use a statically typed language or not is kind of secondary to that. But in the future, I think we'll see more of that. You will write down a specification of what you're trying to do as part of your types, and then your system will generate for them. And that's also a way of proceeding very systematically. So I think when you're teaching programming, it's, being inclusive is very, very hard, right? It's not enough to get people excited. It really is important to impart practical knowledge and competency. And the only way I know how to do this is to teach a systematic approach. You might call it bureaucratic if you're German, but to my surprise, even the Sheldons like this after a while anyway. And we should really refocus, or we need to focus, after all the exploits we've seen over the past couple of decades, on correctness. And I think this is the path to do that. Thank you very much.
Thank you, Mike, for this presentation. We now have like 2 or 3 minutes for questions. Please go to the mics. 1, 2, 3 or so. Ah, we have one there.
Hi, mic on? Yes. So coming from a lot of the software development world and practical experience probably delivering with other customers, have you got any insights into how people would often do teaching by code review, a direction for people to go in reading to learn more about code, learn more about the structure of code in the way that software development often is typically taught? Do you have thoughts on that specifically in this?
So I think it's valuable, but in my experience, it's just not enough, right? So the Sheldons of this world, they're able to figure out how to program by themselves, essentially, right? By just saying, this piece of code is good, that's teaching by example, right? This piece of code is good, and this piece of code is bad, or we can improve upon it. It's just not a constructive way. It's helpful, right, to sharpen the sense of, it sharpens your review facilities, which is an important part of learning anything. But really, I think so in my experience, it's completely crucial to insist that in your teaching methodology, you teach them steps that they can actually follow, right?
Sure, I agree with that. Mm-hmm. But in respect of how many modern software development teams work, in a code review, you can go, this approach will have this and this problem. Have you thought about doing it this way? What have you considered? Do you have any thoughts on that process in teaching people in that process, in that duration?
So for beginners, my experience has been that it doesn't work very well, right? Okay. It's a common educational point, right? That you need to teach people. There are many different approaches, and we're going to we're going to judge them, and we're going to say this one is okay, and this one is maybe a little better. My experience has been with the vast majority of students, right, is if you use that as your main teaching paradigm, the problem is they produce zero solutions. And so it's a much better idea to really insist on that one correct solution, and you can branch out later. Okay. Does that make sense?
Thanks.
Sorry.
Mike one. No, it's okay. Short, quick questions, please.
Well, I hope it's a short question. Thank you very much for the talk. I'm going to crash my brains on what you've told for the coming days. There's one thing very popular among youngsters, which is Arduino.
Yeah.
It's stick up with C and C++, and you get very crappy C code. So how would you put this, what you've told tonight, into the environment of such a popular platform like Arduino?
So I think I would try to make the teaching languages work on an Arduino. I think that's going to be very hard with the really, really small ones, but with the sort of medium-sized one, it might actually be possible. But yeah, as you point out, there's a bunch of crappy C code running on Arduinos. I can see the attractiveness of that approach, but it's not one that I personally prefer.
Could Scratch fill the gap?
No.
Thank you very much.
That was a quick answer. I'm sorry we're running out of time. Thanks for your questions, and thanks again, Mike, for your wonderful talk. The applause.